All right, so we love real world stuff. And one of the hallmarks of EET program is try to give you real world based applications. Well, this is a real world generator. It's Siemens Westinghouse. These are, again, calculated saturation curves, not actual test curves. And you'll see why they were calculated right here. Look at the size of the generator. So not as big as that one that I showed you last week, but 1055 MVA. Would you say that's a pretty big generator? Noah's not impressed. He's like, I've seen bigger. No, that's probably one of the biggest you'll ever come across. If you actually do come across one of these, this is very rare to find one this big. Like I said, there's probably in the US, there might be 100 of them that are this size. So pretty darn big generator, electrical generator. So it's 1055 MVA. Look at its voltage. It's rated at 22,000 volts. Remember, even though it's 1,000 MVA, it's 20,000 volt. Look at the current, 28,000 amps. That's a lot of juice, right? At 22 kV. So this has got some oomph. And anything, that's going to be pushing out this kind of power is definitely going to be three phase, 60 hertz, 1800 RPM, another 1800 RPM, right? So this would be definitely a solid rotor shaft. So this is the round rotor design. Even tells you the short circuit ratio, 0.56 SCR. But again, I've never used that data, so I don't know why they provide it. But here is the calculated saturation curves. And this one is not in per unit or in percentages like they were. Everything was a 1 or something like that. This actually has value. So can you calculate saturated and unsaturated values for me? Is that a yes or a no? Yeah. It's something you should know. What is the bottom graph? Or what is the bottom axis, the x-axis? It is field current, DC field current, right? When we do an open circuit and a short circuit characteristics, we're plotting either the open circuit voltage or the short circuit current. Those are the y-axes. The x-axis is DC field current. And if you remember, when we're calculating these things, we have to pick an IF, and then we get an I from our short circuit and our V from our open circuit, and then that's how we can calculate X. So the only problem is I can clearly see, because it says open circuit saturation or open circuit characteristic, but where is the short circuit characteristic? Well, I did some homework, not much, but I did some. Do you remember when we looked at the generator, the 1500 MVA generator last time? And I said, I don't even know what the synchronous impedance curve is. Look what it's called here. Synchronous impedance curve, also called they actually call it the short, I don't know why they call it the synchronous impedance curve, because it is the short circuit characteristic. Maybe it's better to say, I don't know. But you can even see by the title, they're actually trying to help you calculate the synchronous impedance of the machine. So what you have here, air gap line, OCC, short circuit characteristic. I don't know. This might be the OCC, but you can see it has a 0.0 power factor. So this might be not the open circuit. Well, it can't be the open circuit. Maybe this must be like some sort of short circuit. It can't be short circuit. Maybe it's running it at that current. I'm not exactly sure. I don't know what they're doing with this curve. I'm not familiar with it. I would have expected it. You can see it says the 0% power factor, but the 0% power factor, that's what that curve is. But what does that actually tell us? I don't know. I'm not exactly sure what it tells us. Okay. But even this curve over here, it tells you the synchronous impedance curve, which actually has the short circuit characteristics over here. So we need to get 2 points, don't we? We need to get unsaturated and saturated. So unsaturated, we have to be to this side of the curve. So here's the points I would pick. I can see that this line right here is 5 kV, or not 1,000, but 10,000 amps, right? So I'm going to see where that point intersects, because I know that's 1,000. And I'm going to try as best as I can to stay on that line. And I don't know, right about here maybe is where that value is. So to me, that's around 17,000 volts. That look okay? So I don't remember if it says it on this sheet here, but this is a Y-connected machine. So the voltage that you see over here is a line-to-line voltage. It's across two legs of the generator. So that's that voltage here. If I want to calculate the individual one over here, I need to get the phase voltage. So my XS unsat is going to be 17,000 volts divided by the square root of 3. Remember to convert that to a phase voltage. And I'm going to divide that by 10,000 amps. Okay. Make sense? Still make sense? Not sure? Because that's literally what we're trying to do, is just pick a field current. You can see that the field current over here is, I don't know, whatever that value is. And don't get nervous and say, oh, Paul, that's only, what is that, 0.18 amps. If you look a little bit more, it's times 10 to the fourth, right? So it's 0.18 times 10 to the fourth amps. So it's 1,800 amps of DC field current to provide that. But again, that field current doesn't really tell us anything. And then the next thing I'm going to do, so this curve stops right at about here. So I'm just going to pick a point right here, because that intersects on the, it intersects one of the lines that crosses here and here. So this is my saturated value. And this value over here is, I don't know, let's call that 26,000 volts. And this current over here, sorry, can't draw perfectly straight. That's what, 28, 29. So that's 27,000. Well, I know that I need to be saturated. I need to be someplace above the knee of the curve. And I'm assuming that the slope of the line above the knee of the curve is fairly constant. So it's the best that I can do. Okay. It would be better to go a little bit further away, but you can see that it's kind of rounded the corner already, and it looks like it's leveling off. So it appears that it's going to be straight the rest of the way. But again, that's the best I can do. So I'm going to go with that. So my XS saturated is going to be equal to my 26 kV. Again, I've got to divide by the square root of 3 because I'm looking for a phase voltage. And now I'm going to divide that by 27,000 amps. And those are the two values you have. I didn't even calculate RA. And if I look at the original document that I got this from, I don't think it tells me anything about RA or anything. Let me scroll up a page. Yeah, I don't see, well, maybe it is over here. Yeah, you actually might be able to calculate. You see where it says the direct access synchronous reactances? These values over here, you should get pretty close, except for those are called per unit. And you don't really know how to do per unit yet, but there is a way to check. If you wanted to check, if you multiply this by 22 kV squared divided by 1,055 mega, and you multiply that, you should get pretty close to the same value of what you just calculated. Okay. So let's see. We have some armature resistances, positive, negative sequence. This one would be the closest to giving you RA. But you can see it's 3.55 milliohms. pretty small. So you can neglect it. When you compare that, actually, this is per unit. When you compare this to this, right? This is what, 1,000 times greater. So you can pretty much ignore any armature resistance and get pretty good results.
How do you know which one to pick
Out of those three? Excellent question. These terms will make a lot more sense to you when you start to look at those values. Actually, you know what, we might be even a better one. Here's the DC resistance. Let's just use the DC resistance. Let's actually use this one. So forget about that. It actually calls it RA. So let's use 0.008. It actually tells us. I didn't realize they actually provided that. So it tells us what RA is. So if you wanted to come up with an exact model, you can actually calculate XS directly. But again, 0.0008 is 8 times 10 to the fourth, or minus fourth, versus here, which is 1.7. So it's almost 10,000 times greater, right? The synchronous reactance. So you can pretty much ignore it and still get pretty darn good results. Okay. But yeah, this is real world generator stuff. And for some reason, these big facilities, they keep really, really good data because obviously you want to know everything you can about a 1055 MVA generator. So they keep a lot of this information handy and they obtain it where it's harder and harder to get information for like a small gas turbine. Those aren't always available to you. So I was able to scrounge this up pretty well. Yes, sir.
So what would you said solve for excess directly using RA or using the
Yeah. Because remember Z, this is JXS, this is RA. Z is equal to RA plus JXS, right? So if I have the voltage magnitude and the current magnitude, the magnitude of Z is going to be equal to the voltage divided by the current, those magnitudes only. That is equal to RA squared plus XS squared, right? Square rooted. If I want to solve for X of S directly, X of S is going to be equal to the square root of the magnitude of V over the magnitude of I minus RA squared.
do we have V and I in that?
Yes.
That's those two.
This is V and this is I for the unsaturated value. This is V and this is I for the saturated value. Right?
So we would just use what the 20K or the 27K, or I guess all those greater than 30.
Not the 20K, 26K over the 27K. Don't forget to divide by the square root of 3. And that's for the saturated value. For the unsaturated value, we would use the other one, the 17K over the 10K. Let's check to see how close we are. Anybody have their calculator handy? They can help me out. What's 17 divided by 1.7 divided by square root of 3? Should be almost exactly one, right? 0.98. Okay, now for giggles, if you multiply, if you multiply 1.9215, multiply that by 22 squared, and divide by 1055, what do you get? I would help you along, but I can't because my calculator is still uploading. What'd you get? So the number is 1.9215 times 22 squared over 1055. 0.882. And the other one was 0.9 something. So close-ish. It would be even closer if we did the RA calculation, right? If we pulled out RA, but it probably wouldn't change that much. So what my best guess is that these folks had this to work with, right? They had calculations. We had a pretty rough looking curve to kind of like pick points off. So how accurate can you be? If we could zoom in and it wasn't, whoops, if it wasn't a rough looking curve, we could probably get a little bit closer. But, you know, I don't feel too bad, right? We got pretty close. So I'm happy with that. Yes, sir.
Where is the data come from? The manufacturer? Or the-
Let me show you. I don't have to tell you. From Siemens Westing Power Corporation.
or the-
They calculated it, right?
Okay.
So-
So as a customer, you'd probably receive this entire data sheet.
Well, be careful. The customer may get it, but they should get it if you ask for it. So unless you ask for it, they might not send it to you. Some of the stuff is proprietary. Some of it, they don't want to send you any more information. It takes more time for their part. So they might not send you those curves. They almost always will send you a data sheet that looks like this. Remember that little cheapy generator, that 4 MVA generator we looked at, the one up in Millinocket? That had a similar data sheet like this, but it didn't have open circuit and short circuit characteristic curves. It just had something like this. Okay. Does that help a little bit with understanding short circuit and open circuit? Because you have a homework problem that do that, and you have another homework problem, which is for a real world generator to help you with that. Any questions? You like the real world stuff or do you hate it? It's a lot of stuff. I got this information from a calculation that has 141 pages. So sometimes you got to dig and you got to find what you're looking for. Remember the transformer, open circuit and short circuit, or no load and load loss tests. We had a 100-page document there. That information is there. You just have to have enough background to be able to parse through the information that's provided and see if it has what you need. Okay. So a little bit out of date, right? 20 years old, but they're replacing this generator. They replace it every 20 years. So for nuclear power plants, they relicense every 20 years or so, or they try to get a license. So all nuclear power plants, at least in North America originally, were offered a 40-year license. And after 40 years, they thought, oh, the plant's going to be kaput. But then they realized they had a gold mine because these plants were all built and they're still really well, they're in good shape because they're so well maintained. So let's do another 20-year license extension. And you got to do a lot of work to prove everything's going to be okay. So they get a license extension. This plant is actually going for another 20. So this is going to be a nuclear plant that operates for 80 years, which is very unlikely for most generator applications. Hydroelectric dams, they might have been there for a while, but a lot of times they'll change out the generators just because, it makes sense to do it. Like, I don't know with the Hoover Dam and all the electrical generators there, if they'll continue to do that, but, we'll see. So yeah, this will be a new data sheet because they replace their generator because they try to get a little more out of it. And then they just take the generator, like most electrical equipment, 20 years is a pretty good service life. So change it out and hope for the best, I guess. All right, where is my PowerPoint? There it is. So we'll do a little bit of synchronous motors. I don't have a ton here, but then we have to talk about exam 2. Because after this chapter, we'll have finished all we need. So you all get to decide. And while I'm getting this set up, you get to think about, do you want an exam Monday morning at 8 a.m., the day you get back from break? Do you want an exam Tuesday during class? You'll only have an hour and 15 minutes, but we could do it then. Or you could do an exam on Thursday during class. So that gives you an opportunity to come back from break. We can do a study review session that Tuesday. You don't have to walk into lab at Monday at 8 a.m. and take a test. So that gives you that time, but you only will have an hour and 15 minutes. And I can only do that because other people have classes. I don't know what's going on. So we have to do it during class. And then that week, what I'll do for lab is we won't have lab that Monday. So I'll give you the extra time to study. Anybody want to vote now? Or you want to think about it and decide on Thursday? I need some responses. Or
I would prefer to have it done.
okay.
But I know
Anybody want to do, let's do in class. Anybody want to do Thursday? Raise your hand. How about Tuesday? How about Monday after break? All right, so let's do more voting. So I gotta do polls. Let's see, I'll just edit this one. So exam 2, date. Tuesday, Thursday, Monday during lab. So you get 2 let's just say 3 hours. This one you get 1.25. And this one you get 1.25. The advantage, well, hold on. The advantage of having it on Thursday is we can do a review session on Tuesday. I would have to adjust it a little bit, yes. Hold on, let's do a poll. Let's see what people in TV land say. All right, people, vote away. That's one person. Maybe I guess it's me that hasn't participated. So it looks like it's 10 to 1 to 2. Right. So I think we're going to do it Thursday during class. Okay. We'll have more detail at some point, but and for those of you in TV land, you can actually see this mimics pretty well what was in class in terms of voting. So okay. That'll be that Thursday, yeah, when we get back from break, whatever that happens to be. Okay, so synchronous machine can operate as a synchronous motor or a synchronous generator. Synchronous motors tend to be really big. You can get them really small, like in the case of your alternator. Your alternator actually could be a starter for your car if it was set up correctly, but it actually could operate as a starter for your car. It just would be a little bit of a challenge to make it work. So tend to be pretty big. Like I worked on one that was a 50 MVA synchronous motor. You also see some of them for wind farms because, again, they can provide voltage support that work really well. And you don't see this too much anymore. We have synchronous motors with electric clocks because most of the clocks now are all electronics. You just have a little pulse and you get the results from there. So it operates exactly the same as a synchronous generator. It's just that now you have the net magnetic field chasing the rotor magnetic field. No difference. And so because of that, you get a magnetic field that is rotating inside of the armature windings have a magnetic field that's causing it. And then on the stator, you also have a DC winding that has a magnetic field and it chases it. So it is chasing the magnetic field that you get on the stator. And that produces a torque because the north and the south want to line up. So you'll see here the rotor field will tend to line up with the stator field because they're trying to maintain as much as they can. Again, they can never perfectly line up because you have to have a difference in angle because the torque is there. And that's why you have this larger angle up until a certain maximum is when you get more power out of your machine. So any AC machine, synchronous machine, can operate as a motor or a generator, but the synchronous machine has to operate at 1800 RPM, 3600 RPM, et cetera, et cetera. So there's oftentimes a downside with that because the moment you flip the switch on an AC motor, synchronous motor, it immediately wants to go to synchronous speed, which can be very difficult on mechanical systems. And what we'll find when we look at asynchronous motors, they actually ramp their speed up a little bit more linearly. And so you can end up getting a much better operation. So you don't see nearly as many synchronous motors as you do as induction motors. So the equivalent circuit, sorry, wire there's unfortunate location. Hopefully this comes back on. So The only difference between a circuit is power is going in to a motor, which means the current direction is going in. All right. That's sort of the key difference between synchronous generator and synchronous motor. So the terminal voltage is going to have an angle at 0, and then the angle inside my generator. So this is, or my motor, I should say, this is VA or VT. And then this is going to be my back EMF or my armature voltage that I would see inside the machine. I know that this is a motor because my angle of delta is negative. This is a motor. This is a generator. And the only difference is the torque angle. Positive torque angle, generator. Negative torque angle, motor. The magnitude of EA or EF does not tell you if it's a motor or a generator. It only tells you if the machine is overexcited or underexcited. Okay. And the torque that is that exists, right? Because you're having a motor, so you have to have a torque that's rotating whatever mechanical system you want. You have to have an induced torque on the electrical system so that they will balance each other out. You've got electric power going in, that's being converted to mechanical power, but there has to be an equivalent induced torque because of the electrical power flow so that you can actually provide torque. And that's okay because power equals torque times omega. As long as you have power and you have speed of rotation, you've got a torque that flows there. Here are some cases where we have synchronous motor operation, and you can see EF is always below the terminal voltage of the machine. So delta here is negative, but this is a leading power factor. Why is it leading power factor? Because the current leads the voltage. And what we see is IF is really long, isn't it? Much longer magnitude than here. So if I have a leading power factor, what does my power triangle look like? So S equals VI conjugate, right? P is always positive. Where is Q? Going down, isn't it? Because I is a positive angle. When you take the conjugate, it becomes a negative. And if I take a look at that, if this is my motor, P is going in. What's the direction of Q? It's going out, isn't it? This is an overexcited machine because it's taking real power in from the grid, but it actually is putting out reactive power to help support the grid. So how do you do that? You just goose the excitation system. All you need to do. So this magnitude here of EF really tells you if you're over or underexcited, just like in the case of a synchronous generator. So you can still have the same operation. The difference is, again, our delta is a negative number if it's a motor. If I look here at the bottom, this is underexcited. Why is it underexcited? Well, that's not so obvious, but I have a lagging power factor, right? Because the current lags the voltage. And when I run that through S equals VI conjugate, I get P and Q. So from the motor's perspective, P is in and Q is in. It's underexcited because the excitation on the machine, that field current that's going into the machine, is not large enough to support the magnetic needs that that machine has. So that's why it's underexcited. Over here, it's overexcited because you have more than enough excitation in the machine to support its needs. It's actually dumping it out. And again, that's all dependent on the magnitudes. Look at the magnitude of VT. Okay, so in general, if delta is greater than 0, it's a generator. If delta is less than 0, it's a motor. Okay, all I'm looking at is delta. If the magnitude of VT is greater than the magnitude of EA, it absorbs or is underexcited. If the magnitude of VT is less than the magnitude of EA, it supplies, oops, or is over excited. Okay, so synchronous motors, synchronous generators can operate over or under excited. It doesn't matter if it's operating as a motor or a generator, and that's a huge advantage. Because depending on how the grid is operating, you can say, you know what, I need Q. So that motor can support it, or it can reject it. And in some cases, your synchronous motor is actually better than cap banks, right? Because cap banks can provide Q. The problem with cap banks is they're usually discrete. You're putting out 10 kVAR or 10 megavar, whatever it is. But in a synchronous machine, it can constantly be adjusted so that the voltage is, I mean, the reactive power is maintained at a certain value. And so one of the things you're learning, you're starting to see more and more of is inverters are operated at a specific power factor to meet utility requirements. And the utilities are taking advantage of these things to really support the grid. Synchronous machines have been doing that for 100 years. Inverters have only been doing it recently. So what are applications? Again, they're pretty big because they're expensive to make. But I've seen them for voltage support for wind farms. I've seen them for excitation or for grid support at utility. Like I said, there's one in New Hampshire at Huckins Hill. They're putting in a 50 MVA one. It's very efficient. And it runs at a constant speed. So that's why you're starting to see more and more of these in EVs because they operate at such high efficiency. Again, you can control that power factor just by monkeying with the excitation. And again, if you need 500 RPM, lower speeds, and above 600, a synchronous motor is actually cheaper than an induction motor. But in most applications, you're still going to go with an induction motor because that speed, if you have variable speed needs, it makes it much, much easier for that. All right. So here are a couple examples: reciprocating pumps, compressors, crushers, rolling mills, and pulp grinders. Most of those are pretty limited that you actually see them, but there are some applications. And you can buy synchronous machines. They're available. Come on, wake up. So let's take a look at an example. 100 MVA, decent sized generator. 12.5, 0.85 lagging power factor, 50 hertz. Okay, mix it up a little bit for us. It's a 2-pole Y-connected machine. These two pieces right here tell me what the synchronous speed of operation is. What's the synchronous speed? $3,000 RPM, right? Because in 60 hertz land, it's 3,600 RPM for a 2-pole machine. In 50 hertz land, it's 3,000 RPM. So to get the speed, that's all I need to know. Now, what is the magnitude of the internal voltage at rated conditions, and what is the load angle at these conditions? And then, well, let's see. No, let's do this example here. I thought I had it out, but that's okay. All right, so the first thing I'm going to do is I'm going to draw the schematic. So here is EA. Here is J X sub S, which is equal to J 1.1. And here is RA. I should draw that as a resistor, which is equal to 12 milliohms. And here's my terminal. It's Y connected. But remember this, the equivalent circuit that I have here is a single phase representation of this machine. So this is 12.5 kV at an angle of 0 divided by the square root of 3. Right? Everybody see that? Yes, no? So now the thing is, this is really odd, right? It's 100 MVA. Well, that is the equivalent power that the synchronous motor needs to be able to deliver rated torque to the load. So I have to do a power triangle, right? I know that this is my power triangle. This is 100 MVA. This is the inverse cosine of 0.85. So my P here is going to be equal to 85 megawatts. How did I know that? Very good. Yeah, the power factor is the ratio of P to S. So at this point, whoops, I can calculate I is going to be equal to S divided by square root of 3 times V. And I take the conjugate of that, right? That's equal to 100 M. The angle is the negative cosine of 0.85. Why is it negative? Because lagging power factor. I divide that by the square root of 3 times 12.5 kV, and that's going to be at an angle of 0. So that's my current I going into the machine. Let me go ahead and move this over to whiteboard because I am running out of room on this sheet. I don't want to move, so let's force it that way. Doesn't want to move that way. So now I have what my current is. Does anybody see me calculate that, or they feel like they can do that pretty easily? Anybody want to see the current calculated? Need a hand, yes or no? I can't tell. Yes, okay. So my I is going to be equal to the 100 MVA times, remember that I got to use Euler's identity to enter this in MATLAB, J, actually negative J, times the inverse cosine of 0.85. That's the S, right? That's already taken the conjugate. Now I have to divide that by the square root of 3 times 12,500. We got a parenthesis, I guess, right here. So that's my current. I don't like the look of that. So I'm going to display my current. And this is unfortunate, right? Because I've got 4,000 amps. So probably what would be better to do is just do the absolute value of I. So I'm getting 4,619 amps of current, right? And then the angle of I times 180 over pi, negative 31.78. So my current I is equal to 4, 6, we'll just call it 2, make it easy, at an angle of negative 31.8. That's my current. That's in amps. Now, I'm going to go ahead and solve for EF or EA. Either one's the same thing. And since my current is in here, I'm going to use a KVL loop. So this voltage minus the 2 drops here. So that's going to be equal to 12.5 kV divided by the square root of 3 at an angle of 0 minus I, the 4620, times 12 milliohms. And that'll give me my value of EA. So let's go ahead and calculate that. So I've got 12 E3 divided by the square root of 3. Let's define that as my voltage. Okay. I already have my current calculated up here, so I don't need that. So my EA is going to be equal to my terminal voltage minus the voltage drop across those 2 elements. It was 12 milli plus J oh, I guess I gotta put multiply here. And then here. What's that?
That's one out right into.
Yes, it does make it easier. So that's my EA. Again, not really helpful. So I'm gonna look at the absolute value of EA. It's 3,441 volts. And the angle is minus 56.3. Okay. And let's think about that for a second. Well, our power triangle, if we did this power triangle, here is the P and the Q is both positive. So M has P and Q going in. So the first thing we needed to say, if this was a synchronous motor, delta has to be less than 0. Is the torque angle the negative 56? It's less than 0, isn't it? So that indicates that it is in fact a motor. That's the first part of it. And then the second part is the magnitude of EA less than the magnitude of VT? Well, hard to tell. We said 12.5 kV is the terminal voltage, but that's line to line. So let's go ahead and do VT and redisplay that as a phase voltage. That's 6,928 volts. Hopefully y'all can see that the voltage magnitude for EA is much, much less than the magnitude there. So if I scroll back over, two criteria, delta has to be less than 0, and my my magnitude of VT has to be greater than the magnitude of EA for it to be underexcited or operate at a lagging power factor, which is what this confirms. Okay. Questions? All right, how do we answer the second part of the question? What must the torque be applied at full load? Power equals torque times omega, right? Power, 85 megawatts, is equal to the torque times, it's not 3,000 RPM, it's 3,000 times what? We have revolutions per minute. There are 2 pi radians in 1 revolution. And there are 60 seconds. Whoops. There's 1 minute in 60 seconds. So my torque is going to be equal to 85 megawatts divided by, let's see, 3,000 divided by 60 is 50 times 2 pi. That's how you calculate the torque. Okay. That's ignoring any losses in the machine, not even including armature losses. No friction and windage. That's just the amount of power that needs to be provided. Okay. So here's another problem. 3-phase Y-connected synchronous motor is rated at 120 MVA, 13.2 lagging power factor, and it's operating at 60 hertz. So do I even need the 60 hertz? Unless I need to know what the speed is. No, don't need it. I do need my S here. And I'm telling you what the load is. So let's go ahead and just copy this over to whiteboard. All right, so we're going to build our synchronous motor circuit. So here is our voltage. This is EA. All we have now is J.9 ohms. We're not even going to bother putting an RA because it's so small. Our terminal voltage here is 13.2 kV. divided by the square root of 3 at an angle of 0. So what is the voltage regulation at rated load? Do you remember what percent VR was equal to? Yeah. In here, V full load is V terminal. V no load is EA, right? Because that voltage is being controlled there. So how do we calculate EA? Step 1. We need to do the power triangle to solve for I. Step 2, KVL. To find EA. And once we have that, that's it, right? It's just a two-step process. So the first thing I'm going to do is solve for the power triangle. I know that this is 120 MVA. And this angle here is the inverse cosine of 0.8. So S is going to be equal to 120. Whoops. Why doesn't that want to write? At an angle of inverse cosine of 0.8. That's my value of S. So my I is equal to S divided by V terminal. Don't forget the square root of 3. Actually, no, I got to multiply that by 3. It's 3-phase times the conjugate. Right? It's 3-phase machine. Make sense?
So, but how can S be both 120 and also 120 times the inverse cosine of 0.8?
What did you say?
Oh, it's the angle, yeah, got it.
Did it make sense or no?
Yep, I got it.
Okay. So to solve for I, let's plug that into MATLAB. So I is going to be equal to 120 e to the 6 times exp j times the inverse cosine of 0.8. Now let's actually make it the full Monty. I'm going to call it the conjugate here and do it all the way out. So that's my angle there, right? I've got the 120. That's the magnitude and the angle of S. Now I have to divide that by it was 13.8. And I have to multiply that by square root of 3 because it's a 3-phase machine. I need my parentheses here. Parentheses here. I think I need one more to close it. Let me just make sure I've got it all here. I got that one. I'm missing this one right here. Yeah, I got it all. So that's my magnitude of the current. Magnitude and angle, or the complex number. So step 1, I solve for I using the power triangle. Step 2, now I'm going to use KVL to solve for EA. EA is equal to the current, or I'm sorry, the terminal voltage. So that's 13.8 kV divided by the square root of 3, because everything has to be in single phase quantities, minus the voltage drop across J.09, I think is what it was. That gives me EA. To solve for percent VR, and I'm just going to write VR because if I put percent VR, MATLAB interprets the percent as a comment. That's going to be V no load, which is the absolute value. Well, I got to put parentheses up here. Absolute value of EA minus VT, 13.8. I'll just do 13.8, make it easier. Divided by the square root of 3. I divide this whole thing by 13.8 divided by the square root of 3. And I got to multiply that by 100. So I get a negative 6.6% VR. It's negative because the voltage drops, right? Because all that excitation that I was getting from the system now disappears. So that goes away. Okay. Questions on how to do part A? So the question is, what would the voltage and apparent power rating of this machine be if it were operated at 50 hertz with the same armature field and field losses as it had at 60 hertz? What's changed? Well, if it's running at 50 hertz, the machine is running at a slower speed. So it has a harder time creating the voltage that you need. But the hope is it could still do it as long as the excitation system is rated to put out enough current. So it shouldn't change neither the voltage nor the apparent power rating, again, as long as you can get enough oomph. The power rating is all based on, what the armature current can handle. So that's not going to change. But the Q rating is going to change based on, hey, can I actually deliver enough field current? Will that work? And what would the voltage regulation be at 50 hertz? It's the same, doesn't change. Because the frequency does not affect the voltage there. All right. Question, Aaron, or?
Well, that's okay. When you have something Y connected like that, it just gives you the voltage. You assume Y goes.
This one in general in this class and in your career, the voltage is going to be given to you as a line voltage in almost all cases. And what's that? No, you want the phase voltage because remember, I'm looking for the voltage across here, which is the individual phase. Over here is the line. No, that's okay. And the reason why I think people in industry use line voltage, because if you walked up to a transmission system and somebody told you that's a 345 kV or 345,000 volt line, you might treat it a little bit differently than if they said it was 199,000 volts. Still a lot of voltage, but one seems much, much bigger, right? Almost double the value. So if you talk about it in terms of what you actually see for a voltage, and a potential voltage, which is a line-to-line voltage, that kind of tells people, hey, I got to be, more aware of what's going on and what equipment to use. The only time you don't see it is when it's really obvious. Like if I told you I'm in a 3-phase industrial facility and I said, hey, that's a 120 volt system, you almost guaranteed, no, that's a phase voltage, not a line voltage. Because that's one of those ones where, we just use 120, and that's only because that's what we use here. If you were told 208, then you would almost guarantee, well, if you were told 120, you almost guaranteed know that system is rated at 208 volts. All right. So 208 is actually fairly common in industrial facilities because everything that they have is 3-phase. So I'm not going to put a single phase transformer to feed some loads. I'm going to run a 3-phase transformer because I want my load to be balanced. And then I'm going to distribute that 120 volts wherever I need to. If you go over to the new air engineering building in Barrows, called new, it's 20 years old, but they call it New Barrows. They have a bunch of outlets everywhere. Everything inside the building it's fed from is a 3-phase transformer, and they just move the loads around as necessary. And again, it gives you a little more ability because if you run 208, you have the ability to do 3-phase. Most single-phase loads that need a higher voltage can operate at 208. And I'm thinking of an example. Anybody here know what an electric dryer is, right? That's running at nominal 240. But if you connect it at 208, it usually will run perfectly fine. Maybe not have quite as much power output, but it runs perfectly fine. Same thing with a electric stove, right? Running it at 208 volts, not going to cause any problems. Sump pumps, maybe, well pumps, probably fine running it at 208 volts. Not going to be an issue. All right. So if you got 3-phase, keep it going there. Torque equation. How do we get induced torque? It's all based on our voltages, our speed, our synchronous reactance and that key thing. Torque angle. All right. So in a synchronous machine that's operating as a motor, this is going to be fixed. This speed here is going to be fixed because it's running at 60 hertz. And this is going to be fixed because you built the machine, so you have a synchronous reactance. The only two adjustable ones are EA and sine delta. This one might vary by 20%, but this one can go from 0 to 1, right? The sine of delta can go from 0 to 1. So by taking the angle between B net and BR and either increasing it or decreasing it, that's how you get real torque out of the machine. So in a real world application, if you're trying to put more torque out of, get more torque out of a machine, another way to say that is put more load on it. Well, think about the application when you're driving a car. If you're driving a car and all of a sudden you start going uphill, if you want to maintain the speed, you got to put more fuel in. It's the same thing over here. If you put more mechanical load on something, you have to draw more electrical power. But in that instant, the electrical motor will slow down just slightly to allow those two fields to separate. We don't often think about that or talk about that when we're in an AC land because we talk about everything being in steady state. But in very short bursts, you do get movement of those magnetic fields as you're trying to put out more or less torque. Okay. So here's our phasor diagram. As we adjust our field current, we're either increasing or decreasing EA because our field current goes up. But take a look at IA. This magnitude really hasn't changed. What has changed is we went from unity power factor up to a leading power factor, or we have overexcited the machine. We now can support that. And the only difference we see, right, is these magnitudes were about the same, maybe off a little bit. But now over here, this is much, much bigger. So because VT magnitude is less than EA, we are overexcited. And that forces us to have a leading power factor. V curves, this shows motor operation. Let's take a look back at this thing. So, what do you know? Even on a synchronous generator that's never, ever going to run as a synchronous motor. If it runs on a synchronous motor, head for the hills because there's a really serious problem. But you still provide V curves. Essentially what a V curve is, it's really hard to tell, but you can see this right here is the power factor, and it goes from lagging to leading. You can see overexcited versus underexcited. So this would be a lagging power factor. This would be a leading power factor. And what you see over here is a quarter, a half, 3/4. I don't know why they didn't call this 4 to 4, just it kind of seems confusing. But each of these curves tell you for the more power output of your machine, what happens to that, the field amps that you need to do to be able to produce either a leading or lagging power factor. And you'll notice they all kind of drop, right? Once they get to unity, because at that point, the machine is providing just enough excitation to make the machine work. If it starts to go this way, right? We start to go, the power factor starts to go lagging. And what we see is our current increases because we need more reactive power from the line. In the other direction, our current has to increase as well because we're supplying reactive power to the grid. So the current goes up. So at our unity power factor is when our line current is going to be the least. Okay. And that just shows you as a V curve. And it only is shown for motor operation because these line amps, this is supplied current. You never see V curves for generators. You only see them for motors. But again, they still provide them. I have no idea why they do it for a generator because I don't think you actually use V curves. But if you need to, you know, you can see V curves. And that's hopefully matches up with what we see here. Okay, and you can see each of the different power levels. You're putting out more power and you move up or down on the V curves. So how do you start a synchronous motor? Because if you energize it, it wants to go immediately to 1800 RPM. Like if you were to go to Maine Independence Station, they have 2 gas turbines. Well, you can't start, we talked about that in this class. You can't start a gas turbine by just igniting the fuel, the gas and letting it burn, because it'll burn the actual gas turbine blades. So it has to move away from the heat because they'll melt. So you have to actually get it to rotate. And on the GE gas turbines, they actually start their gas turbines as synchronous motors. But what they do is they can't run it at synchronous speed. So they have a variable frequency drive. They'll take the grid frequency, 60 hertz, and convert it to 1 hertz. And then they'll energize that, because synchronous speed at 1 hertz is 1/60th of 3600, 1800 RPM, right? You're talking 30 RPM, really slow. Not a problem to go ahead and do that. And then once you get it up to 30 RPM, then you take it to 60 and 100, and then you ramp it up slowly so that when you get close to its nominal synchronous speed, then you can go ahead and light off the gas, and then you can get it to rotate. So that's how GE does their 7FA ones, their gas turbines. An external prime mover, why not just take a motor on the output and actually get it to rotate and start it that way? So you know that the ones that are in Northfield Mountain, the ones that we took to that pump storage facility, they actually have little motors on the ends that actually will energize and rotate. Let me see if I actually have that figure that shows that. Let's see. It might not be in here. Not that one. If I have a one line, I might be able to show you what it looks like. I think this is going to work. Let's see. Nope, not that one. Let's try this one. Come on, wake up. Okay, I think if I can zoom in correctly, you'll be able to see the pony motors on this one. I believe it is the case. Starting motor. See the starting motor? That literally is connected to the shaft, and it actually gets the motor generator to rotate. Because when it's running as a motor, and this is a pump storage facility, right? So you're not going to take buckets of water from the Connecticut River and dump it to the top of the mountain. You actually want to have this generator, which has a big, massive pump. Why not set it up so that you can actually suck water up and take it to the reservoir? So this is a synchronous machine, and it can operate as a generator or as a motor. But I need to have this starting motor here to go ahead and get that machine spinning before I hit it with its AC, with its nominal AC voltage. So that's another way that you can start a synchronous machine. There are a second set of windings on the stator windings. They're called damper windings. They help smooth things out. Sometimes you can start them like that. The third option is to treat it as what we call an asynchronous or induction machine, which is exactly what we'll be studying when we move into the next one. So you start it as an induction machine by shorting the field. That's a little more complicated. Most of the ones you'll see, because these are pretty expensive, pretty important, those are the two that you'll see. If it's a smaller application, you might see some damper windings, or you might short the field. But the top two are the most common for most applications. You just get it rotating somehow. Okay. Questions on anything? Because we're finished up with synchronous machines. On Thursday, we'll probably do a shorter than average class, because I know everybody is almost already on vacation, right? Up this last week. Not so much. So we'll do that. And then the plan is on Tuesday, when we get back from Monday, we won't have labs. So you give you that time to get caught back up in the world. On Tuesday, we'll have a review session. And on Thursday, we'll have a test during the class. Everybody in TV land understand or agree with that? Make sense? Yes, sir.
Would you have the review section, like, some stuff up before?
Yes.
So we can look at it?
Yeah, I'll try to get it posted today or tomorrow. Yep. All right. Thanks, Nate. Any other questions or comments from TV land? All right. Have a great day. I'll see you all on Thursday. Take care, everyone.